This will be the final section over chapter 22. This will be section 5. So we're going to look at the concept called resonance here. When these RLC circuits are all have these components in series, the circuit reaches a maximum current at some particular point, and the impedance reaches a minimum. Both of these are done with a particular angular frequency, and that is known as the resonance angular frequency. So this phenomenon is called resonance. So at resonance, the voltage and the current are in phase, and the impedance Z is equal to the resistance R. The smaller the resistance, the sharper the resonant peak. So the lower circuit's resistance, the higher and sharper is the resonance peak. In the current near the resonant angular frequency, omega naught. So let's take a look here at what it's describing. All right, so we've got the impedance of a series RLC circuit, and it depends on the frequency, which we've seen before. So we've got graphs here of the resistance. We've got the reactance here for each one of these. And then as we're putting together the impedance here, we can see how all of these factors are put together to produce this particular function. Obviously, this is done on a logarithmic scale. So current peaks at the angular frequency at which the impedance is least, because if we remember, voltage is equal to the current times the impedance. If the impedance gets to a low point, then the current comes up to compensate. So wherever this hits a low point, the current is going to hit the high point. This high point is referred to as the resonance angular frequency. And here are some other characteristics. This is the angular frequency at which the inductive and the capacitance reactances are equal to each other. So in other words, these two components are equal to each other, and the resonant frequency is equal to this. Now, when the voltages, what happens to the voltages when it is at resonance? The current at any instance is going to be the same in L and in C. So the voltage across an inductor always leads the current by 90 degrees or a quarter cycle, and the voltage across the capacitor always lags by 90 degrees. Therefore, the instantaneous voltages across L and C are always going to be 180 degrees out of phase or half cycle. If the amplitudes of these voltages are equal, then they add to 0 at each instant, and the total voltage is exactly 0. This occurs only at the resonant frequency. Depending on the numerical values, the voltages across L and C individually can be larger than that across R. Indeed, at the frequencies close to resonance, the voltages across L and C individually can be much larger than the source voltage, which is kind of weird. The phase of the voltage relative to the current is given by equation 22.23. At frequencies below resonance, this is greater than this. The capacitance reactive dominates. The capacitive reactance dominates. The voltage lags the current, and that the phase angle is between 0 and minus 90. Above the resonance, the inductive reactance dominates, and the voltage leads the currents, and the phase angle is between 0 and plus 90. At resonance, the power factor, the cosine of this is equal to 1. This variation of phi with angular frequency is done here, or shown in figure 2218b, which I'm not seeing. Let's click on this and let's see it. Well, I'm not seeing. So in a series RLC circuit, this could be interesting. Let's get this. When you vary the inductance of the capacitance, we can also vary the resonance frequency. That's how some older radio and television receiving sets were tuned to receive particular stations. In the early days of radio, this was accomplished by the use of capacitors with moving metal plates whose overlap could be varied to change C. And alternatively, L could be varied with the use of a coil with a ferrite core that slid in and out. In a series RLC circuit, the impedance reaches its minimum value and the current reaches its maximum value at resonant frequency. So this is going to show a graph of the root mean square current as a function of frequency for such a circuit. So if you plug in these particular values here, this curve is called a response curve or resonance curve. The resonance angular frequency is going to be this. As we expect, the curve has a peak at this angular frequency. So in the early days of radio and television, the shape of the response curve was crucially important. The sharply peaked curve made it possible to discriminate between two stations broadcasting on adjacent frequency bands. But if the peak was too sharp, some of the information in the received signal, such as the high frequency sounds and music, was lost. A sharply peaked resonance curve corresponds to a small value of R, and a lightly damped oscillating system. A broad flat curve goes with a value of R in a heavily damped system. So just some aspects of this. There are some problems here for you to work, and as well as some tutorials here. And that's the end of this particular section.